In the last video we looked at polynomial of degree n. So the highest power is n, where the powers are natural numbers, that is positive integers. The coefficients, that is a1, a2 up to an plus 1, are real numbers. We saw that if a complex number z is a root of this polynomial equation, then z bar, the conjugate of z, is also a root. We actually proved that result. Let's look at an example. Now in this example, the polynomial equation is a cubic equation. So the degree of this equation is 3. The highest power is 3. So n would be 3 if we want to compare it to the general polynomial equation. Now we know that 2 plus 3i is a root of this equation, and we want to find the other two roots. Now because the equation has degree 3, it means that there are at most 3 distinct roots or solutions of this equation. So we're given one of them and we have to find the other two. There's actually 3 distinct roots of this particular equation, but sometimes there may only be one root, or well, 2 roots. We could have a repeated root, for example. 2 of the roots could be exactly the same. Anyway, this one happens to have 3 distinct roots. We won't get any more than 3 roots. We never get any more roots than the degree of the equation. So we can use the conjugate roots theorem to help us get the other 2 roots. Well, straight away we can write down what one of the other 2 roots is. Since 2 plus 3i is a root, then the conjugate of 2 plus 3i is another root. So 2 minus 3i is a root. And I will call this polynomial f of z. So 2 minus 3i is a root of f of z equals 0. So that's the application of the conjugate roots theorem. Now, to find the third root, we have to use our knowledge of cubic equations, finding the roots of cubic equations. So let's call c the third root. We can apply the factor theorem to rewrite this cubic equation as a product of 3 factors. If 2 plus 3i is a root, it means that z minus 2 plus 3i is a factor. So we saw this in algebra, although in the algebra section we were dealing with real roots. We didn't see complex roots, but it's the same idea. If we have a root of a polynomial equation, then z, or x minus that root, gives us a factor. We were using the letter x for the variable in the algebra section, so really there's no change here. X is just replaced with z. The z indicates that we have possible complex solutions, and the roots happen to be complex numbers, but it's the same idea. We can get the factors by taking z minus each root. So z minus 2 plus 3i is one root, z minus 2 minus 3i is the other root, and if the third root is called c, then z minus c is the third factor. Now if we multiply these 3 factors together, set the result equal to 0, we get the cubic equation. Now rather than doing this multiplication here, we can get the quadratic factor of the cubic equation by forming a quadratic whose roots are 2 plus 3i and 2 minus 3i. So in the section on quadratic equations we covered how to do that. We write down z, or well, it was x in that section, but it's z here, z squared minus z times the sum of the roots plus the product of the roots equals 0. That gives us the quadratic equation whose roots are 2 plus 3i and 2 minus 3i, which is also actually the result of multiplying these 2 factors together. So it's probably easier to use this rather than trying to do the multiplication. You get z times z will give you the z squared. You'll have z times this root with a minus sign, and then you'll have z times this root with another minus sign. We can put them together to get the sum. Finally we multiply the 2 roots together. A minus by minus gives us a plus. Anyway, we're looking for the quadratic factor of the cubic equation. So by multiplying these 2 linear factors together, we get the quadratic factor Now adding a complex number onto its conjugate is easy. The real parts go away, so we get z squared minus 4z. When we multiply a complex number by its conjugate, it's actually the same as squaring the real part, squaring the imaginary part, and summing. So we get 2 squared plus 3 squared. That's 13. So the I terms disappear. So now we can write our cubic equation like this. So we have the quadratic factor. To find the other factor, that is the linear factor, that's the factor with z to the power of 1 in it, we divide the quadratic factor into the cubic. So let's do that. So I've covered this in long division section in algebra. We take z squared, divide into z cubed to get z. So that's the division step. The next step is to multiply. Z by z squared gives back the z cubed. Z by minus 4z is minus 4z squared. Z by plus 13 is plus 13z. And next step is to subtract. These always cancel. Minus 7 minus minus 4 is minus 3 z squared. 25 minus 13 is minus 12z. Now we start dividing again. This time we divide z squared into minus 3z to get minus 3, and hopefully this is the result. Minus 3 by z squared is minus 3z squared. Minus 3 by minus 4 is plus 12z. 25 minus 13, this should be a plus. Let's bring down to minus 39 here, forgot about that. Minus 3 by plus 13 is minus 39. Subtracting gives us 0, and that's what we want. So we want a remainder of 0, so this is the remainder. And we expect to get a remainder of 0 because we know that this quadratic is a factor of the cubic. So this must be the other factor, z minus 3. So straight away we can see that c equals 3, so the third root is 3. So if we were solving this equation, if we knew the factors and they multiply to give 0, then you put each factor in turn equal to 0. Because we have 0 on the right hand side, we can do that. And if we solve this quadratic equation, we get these two factors, or roots I should say, as we've seen before. And if we put this factor equal to 0, we get z equals c. But well, we know that this is now z minus 3, so we can see that z equals 3. So here are the 3 roots of the cubic equation.